Hello, friends. Welcome. We shall continue our discussion. Last class, we discussed about three-phase drive. Today, we will look at the control of a separately excited DC motor using DC chopper. This need arises when the input available is fixed DC. We have fixed DC. We want to control a motor, a DC motor. To control a DC motor, we require variable DC. So, the approach basically boils down to varying fixed DC to variable DC. Fixed DC to variable DC, that conversion is typically done by a chopper. The input voltage DC changed to output voltage DC but variable. The output voltage can be more than the input, it can be less than the input. Accordingly, this chopper, as you know, is called step up chopper or step down chopper. So, in order to control the DC motor, we make use of a chopper and we change the output voltage of the chopper according to the required performance of the DC motor. So put it systematically, if the available source is fixed DC, then the separately excited DC motor can be controlled by converting fixed DC into variable DC employing DC chopper. The chopper employed can be either reducing the voltage called step down chopper or increasing the voltage called step up chopper, depending on what application we would like to have, what performance we would like to have from the electric motor. Let us look at the speed control of the separately excited DC motor employing step down chopper. Step down chopper is the one wherein the voltage is decreased as compared to the input voltage. Look at the circuit here. We have the circuit, the supply fixed DC of magnitude Vs, DC motor, armature, field. Field is separately excited, armature between A1 A2, and voltage across the armature is VA. A freewheeling diode is used and SCR is used. We require here a control switch, a solid state switch. We can use a transistor or an SCR. In this circuit, we have shown an SCR as the control switch. So, the circuit comprising of this SCR, this part, this is the step down chopper configuration. We know about that already. So, how this circuit works? We know that when we control the on and off of this SCR, accordingly the output voltage from this input we will get or we will not get. You remember that, the chopper operation. Accordingly, the output voltage VA becomes variable depending on the way we turn on SCR and then turn off SCR, the durations of on and off time. That is where we come across this expression, the control approach. Look at this, VA is equal to delta Vs. You remember this expression where delta is what? Duty cycle. VA is the output voltage of the chopper which is given to the armature, hence it is the armature voltage also. This duty cycle is actually the ratio of on time to the cycle duration. T on is the on time, capital T is the duration of cycle, and that cycle duration is the sum of on time and then off time, T on plus T off. So, the duty cycle delta decides the value of VA, and this delta can be changed by changing T on or by changing T nothing but changing T on and T off, or 1 by T being F. 1 by T is actually F, the frequency. By controlling this, nothing but controlling the frequency of switching, we can control delta. There are different possibilities of changing delta. So by controlling on and off duration, nothing but delta of the switch, whatever we are using, here we have shown SCR, the average output voltage VA can be controlled. And this VA, which decides N, results in change in N also. What does that mean? When I change delta, VA will change, N will change. And this delta itself will change either by changing T on or by changing T. Both by these two possibilities. Changing T is actually changing the switching frequency. Okay. Now, if the armature is assumed to be having high value of inductance, then the operation of the chopper can be assumed to be continuous, typically called as continuous conduction mode. In that case, the current will be continuous. There is no zero current there. Current will be always there. And typically, the current will be varying between an upper and a lower value, I max and I minimum. And voltage and current waveforms for the motor armature will be as shown. Please focus on this. The supply voltage is Vs. Vs is constant. Then when SCR is on, Vs will appear across this armature. So the output voltage VA when the SCR is on will be equal to Vs itself. Then when SCR is turned off, that is, it is commutated, that means this part of the circuit is cut off. The voltage across the armature, when this is cut off, what will be that? When this is cut off, the armature is still running. Because it is still running, the stored energy there makes it to run a generator. The current will start flowing here. The current will continue to be there. But that continuation of current is here because of the presence of freewheeling diode. The diode automatically comes into conduction because it gets forward bias, and IA will be there. And when the freewheeling diode conducts, voltage across this is the drop across this, which is very less. Hence, the voltage across this armature VA can be assumed to be 0. That is why during on time, the voltage across the armature is Vs. During off time, the voltage across the armature is 0. Because the freewheeling diode is conducting, and voltage across freewheeling diode which is conducting is almost 0. That's why we have shown this to be this way. Look at this output voltage waveform. Output voltage waveform is of pulsating nature, and this has an average value which is VA. So this shows for some time I have the voltage, for some time I do not have the voltage. If I change the on time and then the off time, obviously the average value of VA will change. Easy to appreciate, na? If I change the on time and off time, on duration and off duration, obviously the average value of VA will change. For example, if I make it continuously on, average voltage will be equal to Vs. If I make it continuously off, average voltage will be 0. So if I make it on for some time, off for some time, average voltage VA will be between 0 and then Vs will be between 0 and Vs. That means VA will change between 0 to Vs depending on the relative values of on duration and off duration. That is nothing but depending on what is that? Depending on relative value of on and off time. What parameter decides that? Delta, the duty cycle. Is it okay? Depending on the value of delta, the VA changes from 0 to Vs. VA will be 0 when delta is 0. VA will be Vs when delta is 1. Good. So now here look at this, little interesting. When it is on time, SCR conducts, current will flow from this DC source into the armature and current rises. At this instant, we stop SCR, freewheeling diode starts conducting. When freewheeling diode starts conducting, the current will still flow in the armature, but it is not from the supply. The current flow is still maintained due to the energy stored in the armature because of the previous running. And as the armature continues to run, that energy decreases. Obviously, the value of IA also decreases. Hence, we get during off time the decreasing current, and this continues. During on time, current increases. During off time, the current decreases. Even before the current becomes 0, we start the next cycle. Hence, the current toggles, oscillates between a minimum value and a maximum value. So, it is this duration wherein the SCR conducts. It is this duration wherein the freewheeling diode conducts. Our assumption is the energy stored in the armature is so much so that the current is sustained even up to this point. Current doesn't come to 0. At this point, when we are triggering the SCR, when we trigger the SCR, even up to that point, current is there in the armature. Energy stored is that much. That means it is a highly inductive circuit, highly inductive armature. Energy stored is more. So the current waveform and the voltage waveform. When the SCR is conducting, output voltage is Vs. When freewheeling diode is conducting, output voltage is 0. Okay. So that being the current waveform, the average current of this armature, maybe we can call it as IA. This is the average current of the armature. Maybe at first approximation we can simply put it as I max plus I minimum divided by 2. Okay. So now here the voltage across the armature is 0 during off time when the freewheeling diode is conducting. That's what we saw there. And during on time, the SCR conducts, and that time the current will be increasing in nature, and the voltage across the armature will be the supply voltage itself. So like this, by using a power conditioner, which is a chopper, which is DC converter, we can control the DC motor speed. We can control the DC motor speed. Is it okay? Now I will give you a teaser. I have assumed the conduction to be continuous. That means during off time the current is not coming to 0. That is why freewheeling diode is conducting for this full duration of off. If it is not the case, If the current comes to 0 earlier than this T, then what will be the nature of the current and what will be the nature of the voltage waveform? Can you try? I repeat my question. Here we have assumed the continuous current mode. If it is discontinuous current mode, what will be the nature of the waveforms? Please try that yourself. So the teaser is, I will give you a teaser. Teaser is what will be the nature of waveforms. Whatever waveforms we have drawn, the same waveforms, if it is discontinuous conduction mode. The operation is discontinuous conduction mode. Will you try this? This is very interesting. Actually, if you can come out with the right answer, that means you have understood the working of that configuration very well. Please try to do this. Maybe you can show me that in the next class, whatever waveform you have come across. Good. So that's as much as the chopper is concerned, wherein the chopper was assumed to be step down. Now we made a mention that the chopper can be step down or step up. Where the step up chopper is employed, the use of step up chopper we find in the case of DC machine, DC motor, and typically this is employed for regenerative braking. And what will be the configuration looking like? This is the armature, field and the source, and this part is actually the step up chopper part. This part is actually the step up chopper part. This part, can you see this? This is the step up chopper. Step up chopper, we have already discussed about this in power electronics, how actually the input voltage is made more by employing a switch. You turn it on for some time, turn it off for some time, and that will give you a voltage which is more than the input, because the expression will be the output of the chopper will be input to the chopper into T by T off. T is total time, T off is the off time, and T off is always less than T. Hence the output of the chopper will be more than the input to the chopper. Here input to the chopper is VA. So the application is, when this motor was running earlier, it was having some speed. Suddenly it is to be braked now. What we will do there? Then we convert the energy stored in this armature, which is mechanical, into electrical, making it to run as a generator by maintaining this excitation, and it produces some voltage. VA is not the applied voltage now, it is the generated voltage. Using this, we feed the electric energy from this armature back to the supply. But for the energy to flow from here to here, for the current to flow from here to here, the voltage has to be more than Vs. But VA is lesser. This needs to be increased. So to increase VA, we use the step-up chopper. And as the motor's stored energy decreases, this VA also decreases. Hence, continuously we need to increase the voltage so that energy flow from this to this is maintained, thereby decelerating this armature as fast as possible. So step up chopper is typically employed where? It is employed in regenerative braking. For what purpose? To feed the energy back to the source. What energy? Energy stored in the armature. Energy stored in the armature is fed back. When the energy stored in the armature is taken out, its speed decreases. After taking it out, instead of losing it, feed it back to the source, it becomes regenerate. That is braking. And this needs to be continuously done, because as the deceleration happens, speed decreases, this voltage also decreases. The stepping up is to be continuously done using this. Now, this equation is very important. What voltage I need so that the energy flows from here to here, how much energy at what rate I will regenerate, I will decide. Depending on that, how much voltage I require, I will decide. Depending on that, how much is to be this value, I will decide. Depending on that, I will control SCR. I will control SCR. So, the turn on, triggering of SCR and commutation of SCR to obtain a particular value of T off, to obtain a particular value of V, so as to obtain a particular rate of regeneration, so that the braking will be as per my rate of braking will be, rate of deceleration will be as per my expectation. Is it clear? So we have used both a step down chopper and then a step up chopper. Now we will quickly look at another application, a drive. It is series motor drive. Drive for DC series motor or DC series motor drive. DC series motor, as we all know, is the one wherein the field coil is in series with the armature. So we can control this motor by controlling its voltage VA. This VA, the voltage is to be DC. Nothing but we need to have a controlled DC. Controlled DC can be obtained from the input electrical using a power conditioner. This power conditioner is typically a converter and a power converter, power electronic converter. This can be a rectifier, controlled rectifier, if the input is AC, so that I will have fixed AC to variable DC. This power conditioner can be a chopper, a controlled chopper, if the input is DC, fixed DC to variable DC. By having suitable power conditioner configuration, we can have variable DC. Variable DC, when given to the motor, will give me varying performance that I can manipulate depending on the expected performance. Now, when it is a series motor, we should be careful, because series motor has something very typical with it. What is that? Series motor. Series motor is typically characterized by very high speed when there is no load, because field coil is in series, current through it is the same as current through the armature. When the armature current is less, when the armature current will be less, when the load is less, the field current also will be less. When the field current becomes less, the flux becomes less. When the flux becomes less, the speed becomes more. So we should keep in mind this possibility, and suitable care is to be taken regarding the possibility of high speeds at low loads. So low load means IA will be less. IA will be less means what? Flux will be less, because it is this current which is setting up the flux, and that means the speed will be more. You remember that characteristic, series characteristic, at the starting we have typically this type of thing. Okay, this is N, whereas this is, when the load is very less, the speed becomes very high. So the series motor drive is typically using a suitable power conditioner like this. Is it okay? So now, before we proceed further, we will just make a mention about the different applications of the DC drives. We have already made a mention. we will just reiterate that once again. Three phase converters are used for three phase drives, and these three phase drives are used for very high power rated machines, DC machines, and single phase drives are low power. Single phase drives are very low power drives. They are typically used for low rating machines. So DC drives are typically used in steel mills, paper mills, where else, in electric vehicles, etc. And the reason for this is they are simple and easy to control. They are simple and easy to control, and accuracy with this simplicity is very high. The simplicity and the accuracy, they are the main signature features of DC drives. They are employed in the situations wherein you require high accuracy but expect the configuration to be simple, like in the case of steel mills, paper mills, etc. And even in the EVs, electric vehicles, they are used DC drives. Of course, the quantum of the DC drive applications has come down, mainly because nowadays we are able to control induction motors also with the same type, extent of accuracy as we do in the case of DC motors. Is it okay? So next we look at an example. Look at this. We will try to solve a numerical. Here you can find the numericals of this type. Are you looking at this? A numerical. Just see what is the statement. What statement it is? The statement is, this is the numerical. A 200 volts, 875 rpm, 150 amperes separately excited DC motor has armature resistance of 0.06 ohm. It is fed from a single phase fully controlled rectifier with an AC source 220 volts 50 Hz. Assuming continuous conduction, calculate firing angle for rated motor torque and 750 rpm speed. Please read that once again and try to figure out how we can proceed here. Please try to figure out how we can proceed. How we can proceed. Please try. Don't fast forward. Please try. I am giving the pause purposely. I am giving the pause purposely for you to try on your own. We will solve otherwise, no issues. But it's important you try to figure out, try to understand the problem and see what is given and how we can proceed. What is given and how we can proceed. All of you take a pen and paper and try it. What all is given, what all is given, and what is asked, how you can proceed. I am giving pause purposely, intentional pause. please. Uh, Not necessary to get the values. You just try to figure out the approach. That's enough. First I will do this, next I will do this, then I will get this. That way. That's what I am expecting. Not the exact values. Not the exact values. Try to figure out the approach. Few minutes, 2-3 minutes I will give. Apply your mind. You are trying? Good. Please avoid fast forward. Don't jump. Use this pause. Use this pause. Take a pen and paper. Try. Few seconds more. Okay. So now look at the statement of the problem. It is a separately excited DC motor. It is rated for 200 volts, rated speed 875 rpm, rated current 150 amperes. Its armature resistance is 0.06. It is fed from a single phase AC source 220 volts 50 Hz through a control rectifier. What type? Fully controlled rectifier. Assuming continuous conduction, calculate the firing angle for the same torque as the rated torque, but the speed 750 rpm. For the rated speed it is 875. Now the speed is to be 750. With the same torque, to reduce the speed to 750, what is to be the value of alpha, the firing angle? That's what is being asked. So we will first show the schematic, the circuit that will make our understanding of the problem very clear. We have single phase AC. You try to compare the way you thought with the solution now. So we have the DC motor. DC motor is separately excited. This is the DC motor, separately excited. So separately excited DC motor I am showing. This is the DC motor, and the armature I am showing. This is the armature. This is RA, EB, and single phase AC. This is actually the, what is this? Fully controlled rectifier, fully controlled rectifier. And the current in the armature, I will put it as IA1. Hence, this I will put it as EB1, and the speed of this armature I will put it as N1, and the voltage across this I will put it as VA1. All these are for the rated situation, and this single phase AC is actually 220 volts, 50 hertz. So for the rated condition, when the motor operating in the rated condition, what will be that VA1 will be 200 volts. You have got that in the statement, na? 200 volts. And the speed at which it will be running during rated condition, it will be 875 rpm. And what will be the current for the rated torque? That is IA1, which is given as 150 amperes. And resistance of the armature is given as 0.06. This will be the same whether it is this alpha or that alpha, that resistance will remain the same. Now what I will do, I know when this is 200 volts at some firing angle of the rectifier with this input voltage, this will run at 875 rpm. Now we want the speed to be 750. Speed is 750. To get 750 rpm, what is to be the firing angle of this rectifier? That is what is asked. So I will now find first the back EMF corresponding to the rated condition, which is simply VA1 minus IA1 RA, and VA1 is how much? VA1 is 200, IA1 is how much? 150, RA is how much? 0.06, which will give me this EB1 as 90, 99, 200 minus 9, 191 volts. I will get this as 191 volts. Now this is during the rated condition. Now at 750 rpm, the second condition. What is the second condition? I will use the subscript 2. So N2, the speed I want is 750 rpm, the second condition. And in the second condition, the torque is the same as the torque during the rated condition. This means, interesting, that's very important, the current corresponding to second condition is the same as the current corresponding to first condition, which automatically gives me the value which is 150 amperes, So I know second condition how much is the current, second condition how much is the speed, and first condition I know EB1. I will use this expression, which is the ratio of back EMFs is equal to ratio of the speeds. Using this I will get EB2 is equal to N2 by N1 into EB1, and I know all these values. 750 divided by 875 into 191. This will be how much? 750 divided by 875 into 191. Yeah, you will get 163.7 volts. You will get this. So once I know EB2, to have that much EB2, how much is to be VA? The VA now will be VA2, the armature voltage, how much is to be? So that I will get this much EB2. This much EB2 I will have to have because I want this much speed. So VA2 is EB2 plus IA2 RA, which is, I know these values, plus EB2 is 163.7 plus IA2 is same as IA1 150 into RA 0.06, which means VA2 is how much? 163.7 plus 150 into 0.06, this is 172.7 volts. This is VA2. What is that? It means I have to have this much VA2 so that I will have this much EB2 so that I will have this much speed. To get a speed of 750 RPM, I have to have this much of VA2. And how do I get this VA2? From this voltage, by suitably having the firing angle of this. That is where I require relation between the input and the output of the full control rectifier. For full control rectifier, the relation is, what is that relation? You remember, for continuous conduction, the output voltage equal to 2 Vm by pi cos alpha, which is 2 times Vm is root 2 times 220 divided by pi into cos alpha, and that is VA2. VA2 is how much we got? 172.7. From this I will get the value of alpha as how much? 29.3 degrees. 29.3 degrees. Now relax, try to feel this problem. If I keep alpha of this 29.3, then from 220 volts AC, it will give me a VA equal to 172.7. If I apply 172.7 here, then the current 150 amperes will give me a speed of 750 RPM. Interesting, na? So here we will have the numericals of this type, typically involving the expressions which we already know, these expressions. Here I took a problem of single phase. It can as well be a problem with 3 phase also. Those expressions what you have already come across, those expressions I have to use and make use of my machine basics. And very important is put a schematic first before proceeding with the solution, so that your approach will be without any faults. Is it okay? Okay, we will stop there. Next class we will continue. Bye. Take care.